I'd like to share with you one of the guarantees that one can prove for the EM algorithm, namely that the likelihood of the data is non-decreasing as the algorithm proceeds in its sequence of estimates. Remember that EM generates this sequence of thetas, theta 1, theta 2, and so on, and each of them is a parameter for the data, for the probability distribution. Now in EM, the setup was that the original goal was that we wanted to get an MLE or a map estimate. So we wanted theta MLE, which was a maximizer over all thetas, of the probability of the data under that parameter. Or a map, or theta map, and we'll talk soon about how to modify EM to get map estimates. So the best we could hope for from EM would be to actually get an MLE. But it turns out, this is not guaranteed. It's not guaranteed that EM will give us a maximum of this function as a function of theta, a maximizer. On the other hand, we do have the following guarantee. So we have the following proposition. The sequence theta 1, theta 2, and so on of EM estimates, the sequence of parameter vectors produced by the algorithm, satisfy the following. They satisfy that they're non-decreasing. It's a non-decreasing function. The probability of x under theta 1 is less or equal to the probability of x under theta 2 is less or equal to under theta 3, and so on. You get the picture? And here, this x, so maybe I should have mentioned that this x here is, it could be a single observation, but in general it's going to be a sequence of n observations, of n sort of instances of the data. Just like in the Gaussian mixture model, how we had n draws from, from the mixture. Something like that. So I'm wrapping all these draws all together into one x. So this is nice because it at least guarantees that we're not decreasing the likelihood, right? If the likelihood function is, it's some crazy thing, and at least as we're going along, we're not going downhill. At least we're going uphill. But this doesn't guarantee us that, like I said, it doesn't guarantee us that we're going to get to a maximizer, a global maximum. Doesn't guarantee that we're going to get to a global maximizer, certainly. And it also, in this form, it doesn't even guarantee that we're going to get to a local maximum. It just says we're not going downhill. But it's nice. It's a nice start, at least. It's a good thing to have. And so let's prove this. It's not too hard. It's a nice little proof. Well, it's not too hard once you sort of see the trick for how to do it, but it's a little subtle. Okay, so the proof is the following. Let's first remind ourselves what the general, and I'm going to use the general sort of setup here for EM, not the specific one that I derived for exponential families, but the general formulation. And the general formulation was that theta t plus 1 was maybe I should say, was a maximizer. It was an argmax over theta of this function q of theta with theta t, where theta t was from the previous time step. And this function q of theta, maybe I'll write it on the next line, where q theta with theta, let me just put theta naught for, just some generic other theta, was the expected value using the distribution under theta naught of the log of the probability under theta of random variables x and z. I'll put these little caps to indicate that z is random here. Given that x equals the actual observation, the actual observed values, little x. So that was this function q. And the E step was computing this, and the M step was maximizing it. Now, it's going to be useful for us to take the log of this likelihood function here. So let's go ahead and do that. Let's call L of theta. This is going to be a key function here. L of theta, let's call the log of p theta of x. And it's equivalent if we can prove this non-decreasing property for L of theta, then that's of course equivalent because log is non-decreasing. And log is a monotone function. So now the first step, we're going to break this proof up into two parts. And the first part, let me call maybe part A. Part A, we're going to suppose that this function L satisfies some, along with Q, satisfies some nice properties. And we're going to suppose that there exists some function g of theta. Let's call it, actually, because I'm going to use theta, well, I'll just call it g of theta. Some function g of theta. Make a little space here. Suppose that for some function g, we have the following two properties. First, L of theta is an upper bound. L of theta is greater or equal to q of theta with theta naught plus g of theta naught for any theta and theta naught. And also, second property, that L of theta, this is, by the way, this is the log likelihood, that's what they call it, equals q of theta with theta plus g of theta for any theta. So this is and. Maybe I'll put that over here. And both of these hold. And now we're going to see why these two properties imply that this is non-decreasing. So the L's are non-decreasing. L of theta 1 is less or equal to L of theta 2 and so on. And let me draw the picture. There's actually a very, very nice little, it's very intuitively simple to understand why this is the case. So let's see what the picture is here. Let me draw, for color consistency, I'll draw this L of theta in this purple color here. So maybe this looks something like this. And, you know, it's kind of crazy. It's doing its crazy thing. That's L of theta. Let me put that over here so it's not confusing. That's L of theta. And down on this axis, this is just a sort of notional axis. Theta is not necessarily one-dimensional, but this is just notionally sort of the picture, the intuition. And now let's suppose, let's define this thing here, the right-hand side of this. Let's define this, maybe I'll write it over here, h of theta to be q of theta with theta naught, actually h sub theta naught, depends on theta naught also, plus g of theta naught. Okay, so that's h, and L of theta is an upper bound for h of theta for any theta naught. So let's think about when theta naught equals theta t. So we're at the generic sort of step here, and let's say that this is theta t. At the generic step, then, this is some function, and as it turns out, this is usually going to be a nice concave nice concave function that's easy to optimize. That's usually the case in EM, especially when you're working with an exponential family. And what does this function satisfy? Well, we know that L of theta equals h sub theta naught, sub theta rather, of theta. And so in particular, when theta equals t, we have that this function, the function h sub theta t, I'll draw it as a nice concave function like this. Let me draw that a little bit, maybe a little less nicely. Looks something like this. Something like that. Actually, I like the first one better. Yeah, that's good. Okay. So that is h sub theta t. And it coincides with L of theta at theta t. That's this point right here. Now, okay, we're at the generic step here in EM. We've got theta t. We have computed this, we've figured out what this q of theta and theta t thing is. We did the E step. That was the E step. We figured out what this was. And now the next step is the maximization step. So we need to maximize q theta and theta with theta t. So over with respect to theta. And maximizing this, well, let's look at it here. Maximizing q of theta with theta t as a function of theta is the same as maximizing h sub theta of t, because this is just a constant. This is just when theta naught is theta t, then g of theta t is just a constant as a function of theta. So maximizing this over theta is the same as maximizing h sub theta naught over theta. So that's, let's make it yellow so you can see it. Yellow. That's the maximizer. And that, by definition, the maximizer, or a maximizer, let's say there's a unique one. Usually for exponential families, it turns out to be unique. And the maximizer is, by definition, theta sub t plus 1. There doesn't have to be a unique one. I mean, if there's not a unique one, then it's obviously, that you would have a different sort of picture. You'd have another peak, but at least you would also, it would be, it would also be a maximizer. So this is just the intuition. I'm just giving you sort of the intuition here first. So we maximize that guy. And then since L of theta is an upper bound by this property 1, this is an upper bound on h sub theta of t. As I drew it sort of suggestively to indicate that this was an upper bound. So then L of theta t plus 1 is greater or equal to h sub theta t of theta t plus 1. That was this point. So that's greater or equal to that. And that is greater or equal to this, because this was the maximizer of this function. And so therefore, in going from L of theta t to L of theta t plus 1, we increased. Okay, so that's the intuition. And it's when you sort of think about the picture here, you draw it out and think about what's going on at each step. I think it's a very nice picture to sort of keep in mind. It makes it very intuitive as to why this works. All right, so that's the intuitive picture. And next we're going to formalize this. It turns out to just be a one-line sort of thing to formalize this, but then we have to show that in fact these properties hold. All right, so we'll do that next time.